L equals 1. Everybody okay? Sure. All right, so for the ground state, that's this one, the 1s state. That would be E sub 1, 0. And so E sub 1, 0, when we evaluate that for this, the correction here, that would be 1/2 MEC squared, and then, well, if we're not doing hydrogen, I guess I have to put this in, and alpha to the 4th. And then we have minus 3 over 4, because that's just 1, and 1 over 1 times 1 plus a half, which is 1 times 3 halves, which is 3 halves. Or 2/3. I got that right? And I add 2/3 to minus 3/4, and I got plus 5/4. Is that right? Can't be right. Hold on. Minus 3/4 times 3 is 9/12 plus 8/12. 9/12 plus 8/12? That can't be right either. What am I doing wrong? All right, I've screwed this up. All right. I don't know what I'm doing. Yeah, 9/12 plus 4 times 2 is 8. Yeah. So I get minus 1/12, right? If I screwed up my arithmetic, in my notes here I have 5/4, and I don't know how I got that. Anyway, it's some number, all right? And for the 2p states, that would be E sub 2, 1, and that's 1/2 MEC squared, Z to the 4th, alpha to the 4th, and then this would be minus 3 over 4 n squared, so that's, n to the 4th, so that's 16, right? Plus 1 over n to the cubed, which is 8, times 3 halves. And by this time, you totally don't believe my arithmetic. What I got for that is 7 192s. I probably should have just used a calculator instead of trying to work out the stupid fraction. Anyway, those are the relativistic perturbation corrections to kinetic energy, and that's all they're looking for.
Dr. Wright, and what about the N2L0? We don't. Because the 2p.
Oh, they only asked for these.
Okay.
If I look at, I should have read this out loud to you. Determine how the energy levels of the hydrogen atom for the 1s and 2p states would appear in the absence of any intrinsic spin for the electron. So I'm just doing 1s and 2p.
Oh, okay.
And that's n equals 2, L equals 1 is 2p.
Okay.
You're right, there's a 0 in there. But they didn't ask for that, so I didn't do it.
Okay. And I suppose just the one on top of the N1, L1, that's a typo. It should be L0, right?
Ah! It's a righto. I wasn't typing. Markero? Whatever. Okay, yeah, all right. Anyway, I screwed up the constant, but all I'm doing is plugging in for n and L, all right? So it is that's silly, all right? And then the other part of this is part B, which is cleverly on the next page. What happens to these energy levels if the atom is placed in an external magnetic field? Okay, so in an external magnetic field, right, B, you're going to have an additional term to the Hamiltonian, which will be a new term. So H goes to H plus B dot mu, where mu is the magnetic moment. Actually, this should be a minus sign, I'm sorry. All right, so mu dot B is E over 2 mcc L dot B. again, in the absence of the electron spin, which we're told to disregard. So the only angular moment, the only magnetic moment this thing interacts with is the orbital angular momentum. And if we take B in the z direction, this just collapses to E over 2mcc L sub z times B. I'm just taking the z-axis to be along B, and we can rename this constant omega, which is usually what he does. Okay, I cleverly called this omega naught. I don't know why. All right, so how are the energies of these two states affected? Well, the energy of this thing won't be affected at all. Because why? Because it doesn't have a magnetic moment, because L equals 0. Thanks to my typos being corrected, or my rightos being corrected. This thing has L equals 0, so, you know, phooey. Oh, that's why I got the wrong answer. I actually put in L equals 1. I can't believe I did that. All right, so this is, that's 0. And then times 1 to the cube is 1/2, so this is 2. So this really is 5/4. So I did the arithmetic right on my piece of paper. I just copied it wrong onto the board. So there you go. Yay! Okay, so that fills us with confidence about this arithmetic, doesn't it? Because when I did this, I wasn't hugely tired. Okay, anyway, so so as I say, first part of part B is that this thing doesn't get affected at all. This one does get affected though, because this one has a non-zero L state. So this has there are 3 2p states, and this perturbation is going to make the energy of them split. They're all going to have the same energy without the magnetic field. So you could think of that as, I don't know, here's the energy. And then it's going to split into 3. Ugh. So it'll split, this will be the, I don't know, L equals 1 state, which will be, the way I've drawn this, higher energy. Oh wait, there's a minus sign. This will be the L equals -1 state. This will be the L equals 0 state, and this will be the L equals +1 state. And then the last thing they want to know is what is the resulting spectrum. And I did not draw the spectrum, but there is an electric dipole selection rule which says that the change in L has to be ±1, and the change in L has to equal ±1, and the change in M, however, can be anything. It can be 0 or ±1. So, yeah. But I didn't draw the spectrum. I guess I should have. Sorry. All right, that's really all there is to 12. Not too bad. Okay, let's do 13. And look at this, I get a whole new board here. All right, so 13 wants to know about the L dot S perturbation. That is the change in the energy state due to the H1 being HSO, and that's 1 over 2 me squared c squared r dv dr L dot S. So this is the spin orbit coupling term, and this comes from, let's see, I was just quoting that at you. Yeah, 1178. This is a copy of 1178, except that we've put in the term, I will get to it. I will get there. I will not get there. can't find it, I'm sorry. Anyway, all right, so, sorry, we want to show this, and we're gonna, okay. So we're gonna start, as he suggests, with 1177, which is that the magnetic field is minus V over C cross E. And where the electric field E is minus the gradient of the scalar potential, otherwise known as the voltage. Well, sort of. I mean, the potential energy is minus E times the scalar potential. Okay, so that gives us that B is minus V over EC cross delta capital V, where capital V is the potential energy. And if the potential energy is spherically symmetric, say that 3 times fast, then the gradient of V is in the radial direction, and then we just take dV dr. In other words, the gradient collapses to being in only one direction, the radial direction, if V is spherically symmetric, and that's sort of obvious. So, as I say, we're following along with their hint on page some or other. Yeah, in the problem, they said to start with 1177, which is on. Oh, there it is. All right. That's page 400. I'm sorry. Okay. Okay. So mu dot B is E over 2MEC S dot minus V over EC crossed into UR dV dr. And taking that in pieces, this is, let's see if I did this right, 2MEC squared R dV dr S dot R cross V. Oh, you can tell the difference between my little v and my big V, can't you? Sort of. Okay. This is my big V. This is my little v. That's 1 over 2 MEC squared R dV dr S. Sort of. Wait, what have I screwed up? All right, I may have screwed up a sign here. I may have screwed up a sign. That might be a minus. Well, no, he doesn't have a minus sign. Okay. So I'm probably right. Oh, no. All right, okay, he might be wrong. I might be wrong, but if I'm wrong, he's wrong too, so I don't know. Could be. Sorry. All right, let's move on to number 14 before I totally make a fool of myself. So number 14, we're supposed to fill in some steps in a derivation that he does. Let's just find that real quick. That's on page, he said he wants you to obtain the states 1192A and 1192B, and those are both on bottom of page 403. So this is problem 14. So let's just go through that just real briefly. So I'm now looking at 1185 to 1186. So 1186, which is at the top of 403, says 2L.S goes to h bar squared m over, excuse me, just m, and then square root L plus 1 minus m plus 1, and square root L plus 1 plus, no, minus m plus 1, and minus m plus 1. All right, so where the heck does this come from? This comes from 1185 on the previous page, where he's saying that 2L.S is L plus S minus plus L minus S plus 2LZSZ. Now, where does that come from? All right. So that comes from, if you've got L.S, L.S can certainly be written as Lx Sx plus Ly Sy plus Lz Sc, yeah? And then we write Lx as, oh dear, I think it's 1/2 L plus L minus, and similarly with Sx. And then for Ly, oh dear. Anyway, you just substitute in what those things are in terms of the raising and lowering operators. I will find that identity for you because I don't want to mess you up, and I'm about to mess you up, aren't I? Must have been way back when we were doing raising and lowering operators. Way, way, way back, right? Where we were doing chapter 3, maybe? Where did we start with raising and lowering operators? I don't even remember.
Yeah, it was chapter 3, I think.
Okay, I can't find it, but anyway, this is how you get that. I'm just much too fumble-fingered today to look things up rapidly. This is how you get it. You just plug in for each of these things. You can see that the 2 out in front is going to get rid of the 1/2, and you're gonna get 2. You're also going to get 2 contributions from each of these, and then the LZ, and similarly with the SY, and so the other terms cancel, and all you get is these. So I hope you can see that, even if I'm a little arithmetically challenged today. Anyway, so this is where that comes from. All right, now how do we get this? All right, well, what we're looking at is if we've got the raising and lowering operators here, remember that the raising operator on a state raises you in m-ness, right? And so why is this a 2 by 2? Because we're only, so these are the guys that are off diagonal. So what we're doing is we're writing the perturbation in the subspace of the perturbation, that is where the perturbation lives, and then we're going to diagonalize that, just like we were doing with the previous problems where we were doing degenerates. Oh, I hope that was clear. It probably wasn't. All right, so right. Okay. If we look at 1186, where's 1186? This is 1186, and 1187. Then what we're going to do is to find we're going to diagonalize this. So we're going to set this matrix. Let me just erase this part. We're going to take the determinant of this matrix minus lambda I. and set that equal to 0 to get non-trivial solutions, just like you do for, you know, any eigenvalue equation. And I'm not going to make a fool of myself by actually multiplying that out, because I'm sure I'll get the wrong answer since today is today. But I'm just, in fact, going to quote 1189, which says that this is what you get. You get lambda squared plus lambda minus L times L plus 1, and that equals to 0. The nice thing is that the radical disappears when you multiply the off-diagonal elements. Okay, anyway, so that means that, solving this, then, you get lambda equals L or minus L plus 1. I got that right? Yes. And then if we put this back in to the matrix that we had, this matrix without the minus lambda, we can get what the linear combinations are that solve this. So it's just like solving an eigenvalue equation that you already know and love. It's only a 2x2 matrix, so you then take the matrix, and I think he calls them A and B, or maybe I called them A and B in my notes, which I've now lost. Anyway, so this matrix without the minus lambda, and then you set this equal to the lambda times A and B, and you solve for A and B. So that's how you get equations 1192A and B, and that's what I'm going to do for you right now. Okay. Oh, here's my notes. Great. Okay, so we're going to so we have our two things here, and we're going to do this one first, just because that's the first one I've done. So then that gives us, if that matrix operates on A, B, and that's now going to equal L times A, B. So that's the thing I'm solving first. So that gives me M minus L times A plus square root L times L plus 1 minus M times M plus 1 times B. And that equals 0. Zero? Wait. Have I put in an additional L? I have. Minus B. Maybe I did this one wrong too. Hope not. Oh, no, I'm fine. I was looking at the wrong equation. I'm fine. Why am I fine? Ah, you asked. Because I was looking at this guy and I was thinking, oh, I've already got M minus lambda. But I don't! This crazy person. So this equation is M, and then this square root thing, and then this square root thing, and then minus M plus 1. Thank you! So when I multiply this thing out, I get M times A, and this garbage times B, and that equals L times A, and that's it, right? And so I took the L over to the other side. Okay, I'm less crazy than I look. Okay, now, all right, so that gives me, all right, so now what I can do is put this in terms of what B is, so that's what I did. So I said B is L minus M times a. Notice I switched the sign around so it would go on the other side. And then square root of L times L plus 1 minus M times M plus 1. And to make this look a little nicer, I let this, radical, the insides of this radical be L minus M times L plus M plus 1. And if you multiply that out, you can see that actually you get exactly the same thing. And why is that nice? That means that I can cancel out one factor of L minus M. So this is B equals square root L minus M divided by L plus M plus 1 times A. And so that means that I can find out what the, if this is B in terms of A, that now I can apply normalization. So I know that absolute magnitude A squared plus absolute magnitude B squared has to equal 1. And since I know B in terms of A, that's just going to be absolute magnitude A squared times 1 plus the square of that, which gets rid of the radical, which is L minus M over L plus M plus 1. All right, and that has to equal 1. So that gives me what A is, and now I know what, since I know what B is in terms of A, now I know both those things. So that gives me that A is square root L plus M plus 1 over 2L plus 1. To get this, all I did was I made this L plus M plus 1. And that's where I got 2L plus 1 because the M goes away. And then that gives me A is equal to this, and B then is equal to this times that. And you can see that the L plus M plus 1 thing just cancels. So then B is equal to square root L minus M over 2L plus 1. Ta-da! And guess what? That's equation 1192A. Whoop whoop. Okay, now I'm going to do the other one. So the way I'm going to do the other one is instead of the L here, I'm going to put in the other thing here, which is minus L plus 1. And so then that gives me I'm just gonna, let's see, I get M plus L plus 1 times A plus square root L plus 1 minus M times M plus 1 times B equals 0. So I'm just going to do it exactly the same way I did the other one. And that gives me B equals minus M plus L plus 1 over square root L times L plus 1 minus M times M plus 1 times A. But again, I'm going to rewrite this so that I can get things to look nice. And that's L minus M times L plus M plus 1. And so this is just the same thing as square root L plus M plus 1 over L minus M times A. Except I forgot my minus sign. There we go. Okay. And then, using normalization, we get 1 equals absolute magnitude A squared times 1 plus L plus M plus 1 over L minus M. And this is the same thing as L minus M plus this. And the M's go away. And I just get 2L plus 1. And so, oh wait. Yeah, that's right. So that gives me A equals square root L minus M over 2L plus 1, and B equals minus L plus M plus 1 over L minus M times square root L minus M over 2L plus 1, and this goes away with this, and you just get minus, minus is outside. Thank you. L plus m plus 1 over 2L plus 1. And that's 1192p. Yay! What do you know? Darwin can do arithmetic if absolutely pressed. Sorry about that earlier confusion. Okay, and that's all there is to 14. Just a little arithmetic, really. Okay. How are we doing? Let's do 15. Ah! Right, so 15. 15 is the Paschen-Bach effect. All right. So we want to determine the effect of an external magnetic field on the energy levels of the n equals 2 states of hydrogen when the applied magnetic field B has a magnitude much greater than 10 to the fourth Gauss. Thank you. In which case the spin-orbit interaction may be neglected as a first approximation. So we're throwing out the SO correction, and we're just asking for the magnetic field effect on the L and on the S magnetic moments. Remember, in the earlier problem, we said, let's just ignore the spin magnetic moment totally, right? So that was in number 12. In the absence of any intrinsic spin for the electron. Now we're putting in that the electron has an intrinsic spin, and also that there's an orbital magnetic moment, but we're ignoring the L dot S term. So we're including the magnetic term, but not the L dot S term. So in this one, so this is number 15. In this one, we are just having a magnetic field term, which is minus mu dot A, of course. And we're going to say that the magnetic moment comes from both the L and the S, but not together. That doesn't come out right. So this is minus, minus EL, and I'm just copying this from the book, 2MEC plus minus E times S over ME times C, and this whole thing is got in. And again, if we take the magnetic field in the z direction, because we have no imagination whatsoever, notice that the constant term multiplying each of these two terms in the parentheses is the same except for this factor of 2. So we can just rewrite this as EB over 2MCC LZ plus 2SC, where those LZ and SC are as usual operators, but B is just along the z direction. And so we're saying that this term is very much greater than H sub SO. And you can see that you can make it as big as you like just by upping your magnetic field. So there certainly does exist such a limit in which that's very large compared to the spin-orbit coupling term. Okay, so if it's very big compared to spin-orbit coupling, then we can just ignore the spin-orbit coupling, which means we know what the energy eigenstates are. They're the energy eigenstates of the hydrogen atom, which are N, L, M, and, or outer product with, the eigenstates of the spin part of the Hamiltonian. So we call those plus or minus C. Now, if there is no spin-orbit coupling, the spin doesn't interact with the rest of the Hamiltonian, which means that the eigenstates of that live in an actual separate Hilbert space from these guys. We can take the outer product between these two Hilbert spaces, so they don't mix. That means we can actually, since we know the energy eigenstates, we can just write down what the energies are. and the energies will be labeled by N, L, M, and by, actually the energies don't depend on M oh yes they do, because we've got a magnetic field, sorry about that. But in addition to N, L, and M for the electron part, the regular hydrogen atom part, we also have M sub S, I guess I should call it. M sub S equals plus or minus a half. So the sort of the spin part that can either be plus or minus. Yeah, right. Okay. So the energies will just add because there's no interaction, right? So we know we have minus mu c squared alpha squared over 2n squared. That's just the bare hydrogen atom. And then we have the energy for this thing. Okay? So this is plus E B H bar over 2 MC, ME, excuse me, C. And then we have the part for the for this part, which is M S. Wait, did I put in the 2ms? I guess I didn't. Sorry. So that will be wait, that can't be right. These just give us M, right? These give us M, and then these are plus or minus 1. Okay. So that's this M, not this M. So I put in both energies, and it just depends on which way the spin is. Okay, so we're specifically asked for the what are we specifically asked? Oh yeah, here it is. N equals 2 states of hydrogen. So for the N equals 2 states, we've got the 2s state and the 2 p states, and this is 2s is of course L equals 0, and 2p is L equals 1. And for L equals 0, this means necessarily that M equals 0, because L equals 0 and M can't be bigger or smaller than L. And that means that this guy just goes away, and all we get are the spin things. So the energies, the added energy is, so this part is just, this part just goes to plus or minus E B H bar over 2 M E C. That's plus or minus, right? And this, of course, is unchanged. For the, well, except you put in N equals to 2. For the 2p states, on the other hand, since L equals 1, M can equal 0 or brain, or plus or minus 1. Again, if M equals 0, that's the all right, if M equals 0, obviously we have the same result. But if M equals plus or minus 1, then notice you can possibly get complete cancellation here, right? So here the additional term is E B H bar over 2 M E C times M plus or minus 1. And when M equals 1, this just goes away, which is actually kind of cool. And that's really all there is to it. So pretty fast problem. Not a lot of dangerous arithmetic. Only dangerous because I'm sleep deprived and that's dangerous for my arithmetic. Okay, let's do 16. The next 4 problems, as he says, are sort of cute tricks for evaluating average values. And so these are gonna take a little while, or at least the first one will. Right? So the first three props, 16, 17, and 18, use a particular trick that is, it can't be used in all cases, obviously, because it can't be used in the last case, but it is a kind of cool trick, so it's really worth going over. So 16 goes like this. Suppose you want the average value of 1 over R for your hydrogenic atom. Suppose you just want to find out what that is. And why might you want to find out what that is? Well, you might want to find out the average potential energy, for example. And the average potential energy is just a constant times this. So how would you go about it? Well, one way of going about it is actually calculating the interval, okay? You can actually put in the wave function, if you happen to know what the wave function is, and just calculate the interval. But there's a cute trick, all right, which we are now going to go through. We're now going to say, okay, suppose we're looking for the average value of gamma times 1 over R, where gamma is some small constant, okay? So we're going to think of that as a first order shift in an energy. In other words, we're thinking of H going to H naught, going to H naught plus H1, where H1 equals gamma over R. Right? And you know, because we've gone through perturbation theory, for a lot of problems, that the first order correction, E1, is always given by the zeroth order state, let's call it NLM, and then the perturbation, and then NLM. So you can see that this is in fact the average value of 1 over R. Okay, I mean it's the same thing when we're asking for if what we want to find out is an average value of 1 over R, that's the same thing as saying, okay, I want the first order correction to the energy if the H1 is proportional to 1 over R. I hope that's clear. I said it as clearly as I could. All right. Anyway, okay. The cute trick is to say, all right, I'm going to write the energy of the full system, E sub n, as En0 plus En1 plus ... So far, so good. I mean, this is always what we're doing, okay? Well, we can think of this as a power series in gamma, because this is the first order, this is the first order correction to the energy, all right? E1, as we were just saying. And the next and higher order terms are going to have they're going to be proportional to gamma to the squared at the smallest. Because why? Because the second order correction to the energy looks like some k not equal, let's call it n. I'll just truncate this to n. K h1 n absolute magnitude squared over E n minus E k to the 0 to 0. And you can see that this goes like gamma to the square. Everybody okay with this? And higher order terms will go like gamma to the cube, and so on. Okay, so you can see that this is a power series in gamma. A power series in gamma. I hope that's clear. Okay, so if we're looking for the first order correction, that is this, right? The correction that we first order in gamma. Well, so then what that means is that we can expand the exact energy, En, as a power series in gamma and look for the first order correction. So what does that look like? So En equals En with no gamma plus gamma times first order correction, delta, first order correction, car. Right? Well, what is this? This is dE sub n d gamma. It's a Taylor series. The next order term would be gamma squared over 2 times d squared En d gamma squared. And I should have said evaluated at gamma equals 0. It's a Taylor series. It's a Taylor series in gamma. It's a trick because we didn't really want this gamma there to begin with, but we can always set gamma afterwards, or get rid of gamma afterwards if we want to. Not a big deal. We're going to get an exact expression for En, and then we're going to look at it as a function of gamma. How do we get an exact expression for En? Because that's the other half of the trick. That's why you can't use this trick for all possible perturbations. But you can use it for any perturbation that has the form of a term in the Hamiltonian. And this does have the form of a term in the Hamiltonian. It looks like the potential energy. So why can you use it that way? Well, now what we're going to do is we're just going to write down what the Hamiltonian is, which is H equals P squared over, did I use mu? Yes, I did. 2 mu minus Z E squared over R with a 4 pi epsilon naught if you really want. Okay. So what are we going to do? We're going to say that this goes to P squared over 2 mu minus Z E squared over R plus gamma over R. That's the full Hamiltonian, H naught plus H1. Everybody still okay? I realize it's kind of I'm asking you to keep a lot in your head at once to go through this little trick, but you'll realize how cute it is once we get done. Okay, so this is the full Hamiltonian. So this is H naught, and this is H naught plus H1. Okay? But this is very easy. I can rewrite this as H naught plus H1 equals P squared over 2 mu minus Z E squared times 1 over R times 1 plus 1 minus gamma. Have I done that right? In other words, all we've done is change the constant out in front of the 1 over R. So what you can look at that is that Z E squared just went to Z E squared times C E squared minus gamma. So we're just going to change Z E squared to Z E squared minus gamma. In the final formula, it's just a constant. Right? So we know the energies for the H naught are E sub n equals minus mu Z squared e to the 4th over 2 H bar squared n squared. So this will just go to minus mu over 2 H bar squared n squared Z E squared minus gamma squared. Isn't that cute? We now have the exact energies for this perturbed Hamiltonian. So all we need to do, using what we were observing before, is take the derivative of this thing with respect to gamma, set gamma equal to 0, and we've got this. And that's very easy. I mean, even I can do that, even in my present day state, okay? To take a derivative of E sub n with respect to gamma, well, that's easy. That's minus mu over 2 H bar squared n squared. Since this is squared, I'm going to bring down a 2, and then I get Z E squared minus gamma, and then I bring down a minus 1 for the using, chain rule. Okay, now I set gamma equal to 0. And this term goes away, and the minus becomes a plus, and I just get plus mu over h bar squared n squared z e squared. Did I do that right? Well, this must be equal to the average of 1 over r. Wow, that was easy. Didn't require me to do any integrals at all. Isn't that a cute trick? Amazingly, it's exactly what I have in my notes. Oh! Think of that. So we've now figured out what the average of 1 over r is, and therefore the average of the potential energy for the hydrogen atom. So the average of the potential energy for the hydrogen atom, well, that's just going to be the average of minus ze squared over r, which is just minus ze squared times the average of 1 over r, which is that garbage. Mu ze squared over h bar squared n squared. Or minus mu z squared e to the 4th over h bar squared n squared. Cool, huh? All right, let's do 17. And you'll see that 17 is exactly the same trick, but done to a different part of the Hamiltonian. So in 17, we're going to find the average value of p squared over 2 mu. Okay, how are we going to do that? We're going to, again, think about this as something times gamma, where gamma is a very small number. And then we're going to say, okay, the Hamiltonian, the 0th order Hamiltonian is p squared over 2 mu minus z e squared over r. And we're going to have that go to h naught plus gamma p squared over 2 mu. So, in other words, this is the same thing as p squared over 2 mu times 1 plus gamma minus z e squared over r. So we can think of this as a changed mu. Again, that's just a number, so we can just plunkle it right in there, right? So we're going to say mu goes to mu over 1 plus gamma. And I hope I've gotten the arithmetic right here, because the mu is in the denominator. All right. So that means that En, which as we recall was equal to minus mu z squared e to the 4th over 2 h bar squared n squared, that's going to go to, remember, we're only changing the mu. So the mu goes to mu over 1 plus gamma. So this is minus mu z squared e to the 4th over 1 plus gamma times 2 h bar squared n squared. So that's the exact energy for this perturbed Hamiltonian. Using the same argument about the power series in gamma, we now say that, the first order correction due to this perturbation has got to equal gamma times d en d gamma at gamma equals 0. So all I got to do now is take a derivative with respect to gamma, then set gamma equal to 0, and then I've got the average value. And let's see if I did that arithmetic correctly. All right, this is what I got. So So this is den d gamma at gamma equals 0. What I get is mu c squared z squared alpha squared over 2n squared. I hope I did that right. What happened to my h bar? Okay, I'm bad. My h bar went away. I'm going to put it back in because otherwise I've got the wrong units. But my notes are actually wrong because h bar can't disappear. Okay, so we now know, okay, that that is equal to p squared over 2 mu, or the average kinetic energy. As you can see, it's actually also equal, just comparing it with this, to minus the total energy. So in part B, it says, use the results of problem A and problem 1116 to show that for the hydrogen atom, K equals -1/2 V. Well, it's right here, all right? K is equal to minus En, and V is equal to 2En, so there you have it. So K equals -1/2 V. Woot woot. And that's all I've prepared for you today. So we're going to have to stop there. Isn't that a cute trick? It turns out that you can take this cute trick one step further, and he does that in 18. As you can see if you just read 18. 18 is using the cube trick not to find the average of a part of the Hamiltonian, but to find an average of perturbation, the spin-orbit coupling, actually. Cute arithmetic tricks are always fun. I'm going to show you, this is not in the book, but I'm going to show you this anyway, Feynman-Hellman theorem. Maybe I'll do that on my recorded lecture. So, also a cute trick. It's called Feynman-Hellman because Hellman originally published it, and then Feynman independently discovered it. And you'd think it'd be called Hellman-Feynman, but guess who's more famous? And that's an example of something called the Matthew effect. You know the Matthew effect? Have you ever read the New Testament? No? Okay. Well, there's a part of the New Testament called Matthew, right? And in there is a line that says something like, to those that have, more will be given, but to those that don't have, even that which they have will be taken away from them. And so the Matthew effect is a sort of a shorthand term in the scientific community for how much easier it is for somebody at MIT to get a grant proposal approved, for example. Or how much easier it is for Feynman to put his name on a formula that was already discovered by somebody else.